right, a rail with the bar here, okay, in a magnetic field that's out of the pole. Okay. And then the bar has a velocity v. Okay, and suppose this rail actually has a resistance R. Okay, and the R doesn't have to be localized over here. The R can actually be a resistance across the loop. Okay, and this rod here has mass M. And let's calculate the EMF of this process and see what happened with the rod. Okay. So as you already know from last Wednesday, that the EMF is just given by minus dE. Okay. But the phi here, also this rail has a weight W. Right. Recall from Wednesday that phi then is just V times W times V. I guess also times T. You can start. In the end, it doesn't matter because we're going to take a rate of change. So you can start that T equal to 0, the bar is over here, right? At the end. So the flux is 0. And the rate of change of the flux then is equal to, take a derivative of this function, you just get V W times V. Okay? And that's the EMF. That is the magnitude. And what's the direction of the current? The direction of the current is going to be this way. The EMF will induce current. Okay. And that's by Lenz's law. It's not really a law, but it's not always been called Lenz's law. So what happened is as the bar moves to the right, you have an increase in the flux, right? And Lenz's law says that induced current will be such that it's going to counteract that, to resist the increase in the flux by generating a magnetic field going in that direction, right? So the current that is that way, or you can also use Lorentz force. If you don't believe in the Lenz's law, then you use Lorentz force. Then what you have is V cross V, right? V plus V. These are the board give you a force F. It's a magnetic force, right? That will produce current. Right? Positive current will in this direction. Okay? So that's the EMF. But what happened here to the board? What happened next? Any idea?
It's magnetic field.
Yes, the current will interact with the magnetic field. Right, so it produces its own, so this is a secondary effect, right? It produces its own force, and it will actually look at it, right? It's a current going this way on a moving bar, or this is a stationary rail, right? So we don't worry about that part. The bar is freely floating on the rail. We do a lot of experiments like that today. Then there's a current here, the current interacts with the B field and produces force in that direction. Right? And that force is a magnetic force, is I plus B, right? I, and B is outward, right? And give you a force that is retargeting, right? I B times, that's the force per unit length, times the length is W. Okay. The rod has mass M. Therefore, the acceleration, I'm going to write acceleration as v dot, right? In the x direction, this is actually equal to acceleration. This is equal to force. This is in the minus x direction. So magnetic force divided by the mass. So it's just I B W over N. Right? But what is the current? The current I, this is just similar to chapter 4, right? If you have an electromotive force on a loop, right? And then there is a resistance over the loop, then the current, the loop, is just the EMF over R, right? We know this from chapter 4, right? We assume that the material is ohmic, so we can write this. And this will be given then by dWV over R. We substitute this into this equation, right? By the way, this is in the minus x direction. So V dot then is equal to minus V squared W squared after doing all the algebra times NR. Differential equation, first order differential equation in time, and has a solution. Dx as a function of time is just V naught minus e to the minus V square omega square over NR. It's exponentially decaying. Right? So if you give it a kick, eventually it will slow down.
I'm sorry, how did you write the EMF as dWV again?
dWV.
Yeah.
Right? It is that.
Oh, sorry.
Yes, yes. Right. Yeah, we calculate this from the rate of change of the flux. Okay. Question on this? Is this clear so far? Okay. So let's do a second example. I'll come back to this on a rail later on, but let's do another example, example number 2. Two current. Right, two current. They can send each. One has a radius R1, the other one has radius R2. Okay, and in this case here, for the purpose of this example, R1 is much larger than R2. Okay, and you give R1 time varying current, I1. Okay, we want to calculate what's the induced EMF on loop 2. Okay. So to do that, first we calculate. So we want to know the induced EMF on loop 2 due to current I1. Right? Okay. So let's calculate the flux inside R2 due to R1, right? So to do that, we have to calculate the magnetic field. What is the magnetic field at R equal to 0? Here I'm assuming that, that R1 is much larger than R2, right? So I can consider that the P field inside R2 will be constant and it will be equal to the field at the center. Right? And then R equal to 0 is given. This is from Biot-Savart law, or this is from even the pre-lab in the lab yesterday, or in the homework. We will calculate that the P at center is mu naught I1 in this case divided by 2 times R1. This is the magnetic field generated by current loop 1 at the center.
If you hadn't been able to make that approximation, would there be another trick, or would you have had to do something really bad, like double?
Yeah, it's a very bad integral. I mean, it's doable. this is the most simple example. I can look at an example using solenoid. But at the end of the day, you always have fringe effect, right? Then you simulate it or do a complicated integral. But the physics is here.
You don't have to actually do it, but where you get that mu naught I over 2r term, like, would you have to use like units on
Yes, you have to use that as well. Right. In this geometry,
Yeah.
you can't really use Ampere's law. Right. Say if you have a sheet with a current like that, then you can use Ampere's law, and then you can argue by symmetry and use Ampere's law. Right. And if you're a solenoid, you can use Ampere's law. Let's see, what other geometry? But if you have a loop, I don't think you can easily use Ampere's law, right? But with a loop by itself, that will become very simple. In fact, you did this in one of your homework. Calculated PV everywhere along the z-axis, right? This is just a special case where you're exactly at the center of the ring, right? And it's given like that. So the flux at loop 2, right, due to loop 1, right, then is equal to just P1 times pi times the area, right? Area of 2, then it's just P1 by R2 squared, right? Okay. And the EMF on 2 is just minus the rate of change of the flux to 1 divided to 1 dt, then it becomes let me completely write the flux. But 1 then becomes mu naught pi R2 squared over R1 to R1 times I1, right? Okay? So this then become minus mu naught pi R2 squared over 2R1 times DI1. Right? These are all constant. Okay? And let me write this constant as M21, and then EMF2 is just minus M21 by 1. Okay? And this constant here is called the mutual inductance. And it has a unit, which we're introducing a new concept here, the unit of mutual inductance M. EMF has a unit of volts, right? And then, so basically the unit is of this, the unit of M is the unit of EMF divided by the unit of the IDT, right? So it's ampere per second. Right? Okay, the IDT is ampere per second. And there's a new name for this. It's called Henry. Henry is also one of the contemporary of Maxwell, after Maxwell. Right after Maxwell. That's what Henry. Any questions so far? So similarly, this here, if I have again the same drawing, right? if I have I2 that's varying with time, right? I1, I2, if I2 is varying with time, it can also induce EMF on loop 1. Right? Okay? And the EMF on loop 1 then is minus M12 Ti2, right? The change in current here, right, produce a change in flux on the big loop, and it can induce EMF on it, right? And
Is this a new problem?
no, it's a related problem. This is kind of like introducing concept within an example, right?
But like, is there still a current I1T?
No, there is no current I1T. I'm just looking at the
other case.
Yeah, the other
It's
case.
just flipped?
Sorry?
So like
It's
R2,
flipped now.
yeah.
Yeah, it's
R2,
flipped now.
right.
There is an initial I1 there. We don't care where it comes from, right? Suppose it's get generated externally, right? And it's varying with time, and it's introducing EMF on loop 2. Now it's the other way around, right? So EMF 1 then is M12 similarly, right? It's just this mutual inductance on 1 due to 2, right? Times the rate of change of the current, right? Okay. And this is more difficult to calculate, right? Because what happens is you have to calculate the flux of B field everywhere, pretty much, right? Not just here. I do create a B field that looks like that, right? And you have to actually integrate the rate of change of the B field along that surface everywhere inside the R1. And that's actually not simple to do, right? You have to calculate the magnetic field of a dipole at this XY plane, right? But it turns out there's a theorem. It's called the theorem of I never know how to say this word. Reciprocity. I always mangle every time I have to say this word. Reciprocity. I'm not going to derive it here. It's not that hard. It's 1 page in Purcell. You should go through it, right? It's an exercise in vector potential. If you understand it, you understand better about vector potential, right? That shows that M12 is always equal to M1. This is always the case, right? So if you know how to calculate it one way, it's completely general, by the way. It doesn't rely on any approximation. I'm not even, Nicholas was addressing that approximation of, well, do I have to worry about the B field variation in loop 2, right? Sure, I'm making an approximation here so that I can actually calculate M21 to have a simple expression like this, right? But in reality, if loop 2 is slightly larger, then this is no longer exact, right? This is only exact in the limit when, this is exact in the limit when R2 is much less than R1, right? But regardless, if you can measure it or calculate it, right, for one case, then in the opposite case, you can always rely on this theorem. Right? And this is a general theorem that just is a consequence of Maxwell equation and vector potential. Okay. Question?
I have a question.
Yes.
So in the first example, like when you have the I1 going around the bigger loop,
Yes,
then
sir.
that induced an EMF on the smaller loop, right?
Yes, sir.
So in that case, the smaller loop would get a current, and
Yes.
then wouldn't that go back on
Right,
the first
yes,
one,
yes,
and then you would have like an infinitely
Correct. You will have this regression, not regression. What is the word? You have this recursion, right? And then you have to find a self-consistent solution, right? But often the case is that you maintain in practical problem, right? I1 is generated by a battery, right? So there's a demon doing the work, right? So when there's a back, we will talk about this next week when we talk about this circuit, right? So in the end, you just put, swap everything under the rug as the work being done by the team, right? The battery is doing external work to maintain the certain current, say, right? And then you can solve for it. It's a completely separate system. But you're right, though, right? I mean, in this case, I'm not considering the recursive effect, right? The I2, I1 generated an EMF on I2, so there is an induced current, right? That will have a back reaction back on I1, right? It's very similar to the example of the rod, the moving rod, right? Like give it a kick, it will slow it down.
Wait, so what you're saying is, if you did this problem, but then you had something making sure I1 stayed the same, then
Yes.
the recursive effect wouldn't happen because
Yes, because something is
something's maintaining I no matter what.
Yes. Right.
So, just to clarify, this inductance would only happen if the current is changing, right?
Yes, the current is changing.
Yeah.
Correct.
Yeah, it's a function of
it's a function of time, right? Yes,
Right.
There is always that.
There has to be flux.
Yeah, but it has to be flux change.
No flux. There's
No flux change. No flux. There can be flux without flux
Yeah, no
change.
flux change.
There has to be flux change. Right.
Right.
Right. But the calculation of M1, M2 doesn't rely on that in itself. It's just this physical variable here is only the current from loop 1 and then flux generated on loop 2. Right? Is that clear? It's just related. Yeah, right? And then you take the rate of change. M21 is constant. So is M12. Okay? So that's as much as I'm going to talk about mutual inductance. Just like in the discussion on capacitance, right? There's a capacitance matrix, and in the end you don't do any problem on it. But you should know about it because you'll talk more about that in physics 110. But I want to introduce a concept of self-inductance. Before time is it? There's a lot of cool demo.
On 9:40.
I don't have much time. So I want to like 10 minutes with the demo and 10 minutes with the intern. Is everybody here? Nobody is here. Yeah, 20 people. I'm sure hopefully they will show up.
Maybe they don't want them.
Right? So
You don't want to know how bad we do.
the concept of mutual inductance, and in light of all this discussion in the past few minutes, lead to a natural little concept of self-inductance. Back to the question by Imad and Nicholas, right? I will do an example if I have time, but simply, if I have a current like this, and a current I is a function of time, right, on just one loop, right, that will create as you know, this will create a magnetic field like that, right? And then it all discloses on itself, right? So this changing current leads to also a changing flux on the same loop, right? So there's going to be EMF. There is an EMF. Right? So this loop always will try to resist the Lenz law, right? Always will try to resist that change in the flux, right? So it will actually create an EMF going in the other direction, right? To resist that. There is an inertia associated with the magnetic field. Okay, and this EMF is going to be given by, again, minus some constant times di dt. Right? Because the flux is proportional to that constant times I, and then the rate of change of the flux, and the rate of change of the flux is proportional to that constant times I dot, right? And that constant is called L. It's a self-inductance. It's the same as N, right? It's in fact as N11. Okay, this is equal to
So the magnetic field that's there is going to generate an EMF.
Yes.
And then the loop kind of chooses the direction of it to counter.
Yes, yeah. It will move in the direction to counter, try to push back on the current, try to change, right? The current try to change in the positive direction, and the EMF will just back that to push that current change away. Right? So if you want to force that current change, then you have to do a lot of work.
I'm assuming that the way you get the current to change in the first place is to have like a changing changing voltage or EMF or something,
Yes, yes.
right?
Suppose you have some other source somewhere else.
Right. So that in this case, like the EMF that's induced, like if you were, because whatever external force is supplying that EMF, like,
Yes,
or wouldn't the effect due to this like be like negligible because like it doesn't, because the other outside source would keep it up going at the
Oh
same
yeah,
rate,
but
right?
the other source has to do some more work, right?
Oh.
And then at the end of the day, you have to solve this self-consistently with the Kirchhoff law. And then you'll see that in AC circuit. Let me just make sure that I have time for the demo. If we finish the demo, then I'll go back to lecture a little bit. So I introduced the concept of mutual inductance, right? And then self-inductance, which is very important for the discussion of AC circuit, right? And let's go to some demo, Faraday's law first, right? Just to make sure that there's no vacuum valve here. It is a galvanometer that can sense current. Right? This is just an example of what you can do with Faraday's law. If I put this on the outside, no. So where is my magnet? Wait, is this magnet? Wait, I got confused.
Yeah.
This magnet, okay. Because some of these are just different material that I don't want to talk about because we're not talking about magnetic material. But you see this magnet has a magnetic field. If it's moving, then it introduces a change of flux. The coil picks it up, right? And then it changes the current. And then this is what is. So if I move it one way, flux goes one way. If I move it the other way, flux goes the other way. Right? And this is actually how you can generate your AC circuit, right? In your wall clock, right? Basically, you have a time-dependent or cyclical flux as a function of time, and then you get your current moving back and forth. Okay? You can do the same thing. So this is with magnet, but you can also do it with electromagnet, right? So this is mutual inductance here, right? This is the big loop. This is the small loop that we talked about, right? So I can change I can actually shut this switch here, right? It will actually introduce a current or break the current in the big loop, right? So give you a change in flux that leads to an EMF on the smaller loop, right? These are two solenoids inside one magnet. See, it's not as strong. Okay, and it's only one way. I guess if I flip this, I hope it's okay. If I flip this, it will go the other way. Hey, how come it goes the same way? Isn't that weird? Oh, of course I'm not doing anything here. But just your hotel, right? Because I'm just flipping this, it doesn't do anything. It's still the same sign of the current. I have to flip it over here, but I don't want to do that here. Okay, you see, this is Faraday's law in action. I mean, this would amaze a lot of people in the 1800s. I mean, with the age of iPhone, it's not that amazing. But, I mean, look at this, right? I mean, if you don't understand what's going on, it's like action at distance. Right? Okay. You feel free to, I guess I was talking to James, he said, I feel free to experiment around and come down here and try it. So, Faraday's law, I'm not going to put this video in here, but this is another example. Oh, let's do that one first. This one is an impressive Lenz law in action. Right? You create a changing magnetic field. And then what happened? It created a flux in this aluminum pan. This is kind of heavy. See, it's pretty heavy, right? It's pretty heavy. Right? It generates an eddy current, right? Because EMF, changing flux create an EMF here, and by Lenz's law, it will create an EMF in such a way that it will counteract the change in the flux. And when, as you know from your daily life, right, if you have two magnets, north and south, right, north and north will repel, right? So what happened this way, this aluminum pan here will get repelled by the electromagnet, and it will lift itself up, right? So this is
oh my god!
I gotta take a picture of this. Hold on.
What?
This is so
sorry
weird.
guys, I didn't expect that.
Oh, like, I guess we were expecting it, but
It's like, can we put something in between?
So yeah, you can put whatever in between, and then it's not going to do anything because magnetic field just passed through.
Oh, so cool.
Isn't this cool?
Yeah.
So this is a pretty strong. Yes.
Oh wait, can you like
You can try it.
push on it?
Push on it.
Why does it not like fall off?
What?
Why does it not fall off the side?
Oh, it's actually much more complicated. The
Oh my
field is
God.
actually always.
This is really cool.
You can explain it as if it push this way. If it's not too far, the eddy current is such that it move it back. It has a pretty complex magnetic field underneath it. It's like 6 electromagnets in
I know.
Basically all our
But you're right, but otherwise
Can we do this?
that was dangerous. I should have put it in here. I could have killed you with this thing. Like,
Yeah,
cut you.
Are you gonna do it off?
And I cut myself the other day falling.
that's not
Okay, so
good.
it's creating a thing like
Yeah, an
this.
eddy current. There is a changing flux. It creates an eddy current. By Lenz's law, it creates an eddy current in the opposite direction.
It's being
Right?
created on
And
the
then- Okay, it gets too hot. Oh, there's one more. We talk too much because the eddy current generated actually make this thing hot enough. If
Yeah,
I actually do this close to bring this closer by pushing it on with that, which maybe I'll do next. You can actually boil water. Right, this is the water.
No way.
You pour water in there. It gets really hot because this eddy current create this thing has a resistance, right? So I square R, right? It gives you joule heating, right? It gets really hot and I actually can boil the water. I haven't seen it yet. Anyway, maybe
Let's just give it a break. Yeah, let it cool down. Yeah.
That was really cool.
Oh my god, like it worked, right? And like it,
YouTube videos and stuff.
just like, oh yeah, I guess that happens. Maybe magic. Maybe it's magnets. Maybe it's Maybelline.
Again, similar kind of idea, except it's much more controlled, right? Here, you can analyze this with Lorentz force, just like we did during the discussion section when we talked about semi-infinite solenoid with a flaring B field, right? That creates a Lorentz force, right? But you don't have to even analyze it that way. What you have is by Lenz's law, there's a changing flux, right? And then there's an induced EMF by Lenz's law is going in the opposite direction, and then we repel this and propel this upward. Right? And it can be dangerous too. And this is liquid nitrogen. It has nothing to do with the high temperature superconductor. It's for something else, but let's do a simple experiment first. There's a lot of these things here. I don't even know. This is copper, this is lead, this is brass, this is aluminum. Well, I think they put up this aluminum. Let's try the aluminum first. It doesn't do anything.
Maybe it's not.
Whoa!
Just see it? I didn't see it, but it's actually broken. See?
Yeah.
So there is no cut. This is actually has infinite resistance.
Well, that's like, but it does have to get close to.
but this is a complete loop, so current can circulate.
Yeah. Oh my gosh.
You guys are taking pictures of this and all this on YouTube.
Ah.
Perhaps this is actually, oh, maybe if I actually dip it in liquid nitrogen, this is kind of heavy. I don't know what's the resistance of lead, you know, but it gets hot. It actually gets hot. So there is an induced EMF, right? I mean, you don't see it in action, like, you know, jumping up, but it's hot.
Whoa. That was hard.
Copper, right? Copper has very low resistance.
I was looking at so much in wire.
So you have a lot of current. I don't know about glass.
Yeah.
This is actually a good test of you can use this to measure resistance of an heater.
Oh yeah, by how high it goes.
Depending on how high.
That'd be fun. We should do that experiment. Wow.
This brass is actually pretty resistant. See, it gets
shine.
hot. You guys can go down there if it gets really hot. Right? So, I did not actually do this.
What is that?
This is liquid nitrogen.
Oh. What the heck? What?
Okay, that's good. Okay. And then this is the part
I
that's
don't have
dangerous. I think. So I'm going to dip the copper in liquid nitrogen to lower the resistance. I shouldn't do it for too long.
The copper? Not the.
You know, I hope you cover my insurance. I'm not a very good experiment with this. You should try
Do the lead.
Yeah, do the lead.
do with the wet, right? Do it with lead, right?
Coffee.
Can I do it with lead?
Oh god.
No, lead is heavy. I don't want to catch it. It's really cold. Right? I don't want to do it with lead. So it's really heavy. But let's do it with copper again. It's cold. It's really cold.
Can I touch the smoke?
I'm going to look ridiculously embarrassed.
No, this is good. This is good.
Okay, well, with that, let's boil some water out of it. So, hopefully this is actually has cooled down enough. Oh.
The.
I can't do it. I'm not strong enough.
I'll do it. Help. Yeah, have Abigail help.
You can boil water.
Yay!
It's kind of scary. Somebody else do it.
Okay, you just have two people and put the bar.
Yeah.
What are you trying to say otherwise?
Because it actually requires actually some force. Oh yeah, that's another experiment you can do. You can flip it, and then actually the force is a lot less because it's farther away, right?
That's what the copper rings are.
It's hard. If you flip it, if you flip it because of the curvature, you have less eddy current.
Why would the bottom?
No, because the bottom is closer, right? No, then the flux is more flux. If you flip it around, you have less flux.
I appreciate this.
Okay, guys, now it's
Oh, this
I can do some more demo as
Oh, it's cold. Why is it? Oh, my finger. But what does that even mean? Are we supposed to breathe this?
Don't breathe this.
Yeah, what was the average? Just so that we don't let us look